This is the second extra titration curve problem. This problem involves periodic acid, and I want you to draw a titration curve. I have the graph on the next page, and when we get to the graphing part, I'll pull that out. But we're going to graph it using minimum points, which is 4. And in addition, I want you to work these 2 points. Now, these can be used by you to flesh out your graph or not. I'm not going to put them in the graph, but we will work them. Okay? So, what we need to do when we're starting with is identify the 4 points. First thing is point 1 will be 0 base added. That will make it a weak acid problem, also known as a Ka. And we have the Ka given. Okay. Point 2 is going to be your midpoint of the buffer zone. And that's when the concentration of the weak acid amount equals that of the base, so therefore the pH is equal to the pKa. Okay, point 3 is our problem child. That's at the end point, which is the equivalence point, remember, and that's when moles of acid equals moles of base. And then the last point, point 4, and I'm going to come down here and do point 4 just because it's easy to do, is the strong base. You've reached the strong base, and there are 2 ways to do it, and we'll work it both ways. So what I've kind of done is compartmentalized so that I've left myself, hopefully, room to work. If not, I'll work on an extra sheet. These are the things that we need. A couple things we want to start off with is I want to know how many millimoles we have. So we have 13.608 millimoles of our acid, and we're going to need our pKa later, so I like to just go ahead and solve for it. So it's 1.6383 is our pKa. We've got our pKa, we've got our millimoles of weak acid used, and we'll need that for the equivalence point, and let's get started. So for point 1, simply a weak acid, so we're going to have HiO4 equilibrium, H plus IO4. This is weak, so we just need an ICE table. Alright, so initially we have a 0.280 molar solution, 0, 0, minus X plus X plus X, because we're adding over here, 0.280 minus X, X, and X. So this is a Ka, which means it's going to be X times X, or X squared, over 0.280 minus X is equal to 2.3 times 10 to the minus 2. When we do our algebra, we get X squared plus 2.3 times 10 to the minus 2X minus 0.00644 is equal to 0. So we're going to solve for X. X is equal to 0.0695694 molar, which you know is the H plus concentration. So all we have to do is take the negative log of it and determine that the pH is 1.1576. So at point 1, we have a pH of 0.1576, and the milliliters added of base is 0. Okay? So We're done there. So we're going to do point 2, but before we do point 2, let's look at point 3. Well, we said the moles of the acid have to equal the moles of the base. So in order to get the moles of the acid, that's going to be our volume, 48.6 milliliters of acid, times our concentration, 0.280 molar acid. Whoops, we'll put that up there. Acid is equal to concentration of our base, which is 0.160 molar, times our volume. So this is the base side. So what we find out is that X comes out equal to 85.05 milliliters of sodium hydroxide being added. That being the case, we're going to pause back, go back to 2. We know that the midpoint of the buffer zone is the point where the volume is halfway to the equivalence point. So that means the equivalence point, 85.05 milliliters, divided by 2 is equal to 42.53 milliliters. So there's our volume. We know that the pKa, we've already solved for, is equal to 1.6383. So for this one, we had the volume of base and the pH. Here we have the volume and the pH. So we're actually now done with point 2. Let's go back to point 3. Well, point 3 is strictly, as we said, the salt, so it's the conjugate base. So we're going to have, I'm doing it again, let me give myself a little more room here, for minus plus water to produce HiO4 plus OH minus. We're going to need an ICE table, which means we're going to need the concentration. So the concentration of IO4 minus is going to be equal to the millimoles, which we know as 13.608 milliliters, over the total volume. Well, we add 85.05 plus 48.6 and we get our new volume of 133.65 milliliters. Now remember, this is the new total volume. So that we find out that our concentration of IO4 minus is 0.0101, excuse me, not 0.0. I added an extra 0 in there, so 0.010818 with the 18 repeating. So when we put it in here, we're going to put it in as 0.1018. Initially, we've got 0 of the product. We're going to lose X, gain X, gain X. 0.1018 minus X, X, and X. Okay, so this is our KB, which is equal to X times X divided by 0.1018 minus X, which brings us back to, wait, what's our KB? Well, our KB, remember, is KW divided by KA, which means it is equal to 4.3478 times 10 to the minus 13th. Ka times Kb is equal to Kw, and remember KW is 10 to the minus 14th. So we do the algebra and we get x squared plus 4.3478 times 10 to the negative 13x minus 4.4278 6, 9 times 10 to the minus 14th equals 0. We do our math and we find out that x is equal to 2.1040 times 10 to the minus 7th. Now remember, that is the hydroxide ion concentration, so we take the negative log of that and we find that the pOH is equal to 6.6770, which means my pH is equal to 7.3230. And again, we got our concentration, so at 85.05 milliliters of the base added. Okay, we're going to come back and work those extra points in just a minute, but right now I want to go ahead and graph it. So in order to do that, we're going to give you your handy dandy little graphy paper. Okay, and when we do this, my charts always have 14 pH units. So the pH always goes on the y-axis, and the x-axis is milliliters of base, in this case sodium hydroxide. So you want to use as much of the graph as possible, and so you kind of want to count. We know where our equivalence point is about 85, so we need to get past 85. So let's see what happens. 5, 10, 15, 20, 25, 30, 40, 50, 60, 70, 80, 90, 100. Okay, that's good. So let's do every bar is 5. So that gets us 50. And it takes a couple minutes to do this, but it's better to think about it and do it ahead. And if you have to, you can use only half the page, but try to use at least half the page. And I forgot to mark this, so 4, 6, 8, 10, 12, and 14. This is your pH point. So all we have to do is graph the 4 units. Well, the first unit is 0 volume and 1.18. So it's about right there. Now, for simplicity's sake, I'm just going to write an arrow and say 0 milliliters, because that's your X value, 1.158 pH. Now, I'm just going to put it out of the way so I could see it. Our second point is at 45.525 and at 1.6. So we really haven't kind of moved far. So that's about right there. And again, I'm going to designate that point just by 42.525 milliliters. The pH of 1.638 pH. Alright, hopefully I didn't get in my way. Okay, and now our third point is our equivalence point, which is 85 milliliters, and we're at 7.323, so about third way up. So here we go. So I'm going to designate this one over here, 85.05 milliliters, 7.323 pH. Okay, and then our last point, we didn't do our last point, did we? Nope. Oops. Alright, let's go back and real quick do our last point. Well, there's the easy way, which means the maximum you could ever reach, and you'll never reach it because it's a dilution problem, is the concentrated. So our max will be the 0.160 molar, which if we take the pAOH of that gives us 0.7859. So our pH is equal to 13.204. Okay, that's the easiest way to do it. Or you can pick a point. If you pick a point, so for example, I can pick any random point, but let's say that I picked one where I added 15, let's see, how many millimoles? I have millimoles there. Let's say I added 15.2 milliliters. I'm going to pick 95 milliliters. Okay, 15.2 millimoles. Alright, and remember I have to subtract the 13.608 millimoles of my acid. So I'm left with 1.592 millimoles over my new volume, which is 143.6 because you had to add the original, which is 0.01108. Okay, so I'm going to steal this little section here. My pOH then is equal to 1.9552. My pH is 12.0448. Now, if you'll notice, yes, there's a large number difference between here, but it's only 1 unit. And when you're at this high of a pH, it doesn't really matter. So, if the point we want to use is the 12, and we'll just use the 12, that's at 95 milliliters. So we come back up here to the 95 milliliters, and at 95 we have a pH of 12. So here's our 12. Here's our 95. So we're going to intersect here. So this point is 95 milliliters, and my pH is 12.0448 pH. Now, because this is a weak system, alright, there's not much of a change here, but you want to show that it's going to rise and kind of level off, and it's going to get higher as it goes towards the inflection. And the inflection is kind of sharp, and then you're going to level back off again. So your curvature, and it's easier for me to draw it in dash. I'm not really sure why I could draw a straighter line, but notice that there's an up curve that kind of levels off, and you don't have to be a graphic designer to be able to do this. Okay, so there's our graph, and there's our 4 points. Now, the other 2 points that I asked you to do. Oh, one other thing while we're at it. One of the things I asked you, and you'll be given the chart so you don't have to memorize it, is what is the indicator? Well, the indicator is a function of your pH. So your pH is 7.323 at your equivalence point. So let's find an indicator that falls in there. Metacresol blue looks like it'll work. This one's a little low. You could kind of get away with, bromethymol blue. You kind of get away with metacresol purple, but it wouldn't be ideal. So our best bet is bromethymol blue. So if you were asked for an indicator, you would just write indicator bromethymol blue. Now, if you were to pick metacresol purple, you don't have to say the second one. I'll know which one as long as one of them meets it. You can if you'd like. And so we're done with that part. Let's go back to our 2 extra points, and I'm just going to bring in an extra sheet here. We know that the equivalence point was at 85 mils. So both of these points are below that. So both points A and B are buffers. So for simplicity's sake, I'm going to use the same equation so I don't have to keep writing it. Alright, and this time I'm going to add the hydroxide in second because I didn't leave room. So, and I'm writing in pen, and you get the byproduct of water. So I'm going to do A first. So my IC, well, I don't have an IC table. I have my initial and my final. So I know that for the first one, I'm going to be adding 5.52 millimoles of my base. And I know I started with 13.608 millimoles of my acid, 0 here, so minus X. Oops, not X, minus 5.52, because this, we know our specific amount. And we're going to gain 5.52 here. So when we're done, we have 8.088 millimoles of our acid, 0 of the base, and 5.52. This brings us to our pH is equal to the pKa plus the log of the base form, which is iO4 minus over HiO4. So we're going to say that our pH is equal to 1.6383 plus the log of 5.52 over 8.088. Again, millimoles cancel. Again, we don't have to go to molarity because our volumes cancel. So we do our math, and our pH is equal to 1.4724 for A. For B, I'm going to use the same equation, except this time we're going to use 10.272 millimoles of our strong base. We're going to start back with our original amount because this is total, not added in addition to. So we're going to lose 10.272. We'll lose 10.272 here and gain 10.272. Again, we've converted all of the strong into the weak form, and we're left with 3.336 millimoles. Remember, these are all millimoles. So we're back to pH is equal to 1.6383 plus the log, and this time it's 10.272 millimoles over 3.336 millimoles. And our pH comes out to be equal to 2.127. Now, our pH is risen. We're getting close to being out of the buffer zone because the buffer zone is plus or minus 1. So at 2.6 we'd be out of it, but we're still in it. So these are the 2 extra points which you can add to the graph if you like or not. But these are the 2 buffer problems.